Yeah, this is Moses Chibueze, and I'm going to be explaining briefly mathematical induction. Now, what is it all about? This is just a unit you will see in every 100 level or elementary mathematics after O level, and it's basically just if a result is true for any natural number, and then let's say it's true for 1, and then is valid for any other natural number k, we now test if that is valid for k plus 1, and if it is valid, then that formula actually is valid for all natural number. So for each element in natural number, you remember we use n to denote natural number. Now for each element, let's say n in a natural number, now we now test if, based on the properties of the mathematical induction, there are 3 things you test, and if it is satisfied, if it is valid, then you now say it is valid for every natural number. Now, number 1, you have to test for p of 1, and then if it is true, you now test for p of k. Now you assume that this is true, you just assume that it is true, then you now test for p of k plus 1. Now if also true, you now say that then p of n is true for all n belonging to the natural number n. Now basically you understand this from example. Now let's say that you have set of natural number. You now say you have set of natural number and you want to test of p of n. Now you note you have to test for p of 1, you have to test for p of k, and finally you now test for p of k plus 1. 3 steps you need to take. Now for example, if you have this is a series 2 squared then plus 3 squared. Now you have it up to n squared. Now you want to test if actually this formula governing this set is true for every natural number. Now you say that this is governed by this. Now you want to test if it is true for every natural number. Now simply let's do this. If we say you want to test the solution, remember, note 1, we have to check this p of 1. And what do we need to do is just to come to this place and test. You have p of 1, so you have n on the left hand side. This side of the equation is called the left hand side. This side is called the right hand side. Now remember, at every point in time, this side must be equal to this side. So you have 1 squared. So we need to test the other side. Will this side give us 1 squared? Anyway, you see n here, you insert what? 1. So in this formula, we'll just say this is n, this is 1, into this is n, now it's 1 plus 1, then we have 2, this is 1, then plus 1 upon 6. So here we have 1 times, here we have 2, here we have 2 plus 1, that's 3.3 all over 6. So here we have 6 all over 6, which is equal to 1. So the left hand side is equal to the right hand side. Now simple, you just test for p of k. Now as I say, you assume p of k, you just say k squared now should be equal to k into k plus 1. Then you have here 2k plus 1 all over 6. Now next step, you test for p of k plus 1. So it's very simple. We now test for p of k plus 1. Remember, you now said since you have 1 squared plus 2 squared plus 3 squared plus, you now have now k squared. Now the next thing you are going to test now is k plus 1. Now you treat this as one entity squared. Now this should give us, remember our formula, n into what? N plus 1. Then you have 2n plus 1 upon 6. Remember, this is what we are trying to get. So all you need to do is to insert k plus 1. Remember, we were here, we have 1 squared plus 2 squared plus 3 squared up to where we stopped at plus k squared. Now, and I said when we stopped at k squared, we had, anyways, here we just put k, we have k into k plus 1 2k plus 1 upon 6. Now we want to test for k plus 1. Then if we want to test for p of k plus 1, remember we just have to do it the same thing. Two ways. You can do this in two ways. You can insert k plus 1 throughout here like this: 1 squared plus 2 squared plus 3 squared plus 1 2 3 plus, you have k squared. Then the next one you now say k plus 1 as one entity squared. Now you have added it to the left hand side. Now let's do the same to the right hand side. This same entity, let's add it to this other side. So we have k into k plus 1. Then we have 2k plus 1 and plus k plus 1 squared all over 6. Remember, we added this to the left hand side, we added it to the right hand side. No cheating. Now let's consider the right hand side. Now we'll consider the right hand side. The right side. Now this is we equal to, when you look for the LCM, here you have k into k plus 1, and you have plus 1, then plus, you now have 6, you now have k plus 1 squared, and this now will be all upon 6. Remember the LCM here is just 6, so you have this straightforward just like that. Now remember, since you have k plus 1 here and you have k plus 1 here, so you can factor k plus 1 outside. So here you have k plus 1. If you factor it, and what will be remaining here, you just have k multiplying this, so you now have 2k squared. This one is outside, k squared, this k multiplied by 1, you now have plus k. Then I have plus 6. But remember, you factor out only one of this k. This is square, you only factor out this outside, so you still have here k plus 1. Remember, you only factor out this term out here, so here you are left with 2k plus 1. Multiplying this k, you have this one, now you have this upon 6. So what are you left with? You now have k plus 1 into 2k squared plus k plus 6 times k, 6k, then plus 6 upon 6. You're left with k plus 1, 2k squared plus 7k, then plus 6 upon 6. Now remember, what are you even trying to do? You are just trying to prove that for k plus 1, this formula still stands. So you want this formula to look like, here you have k plus 1, here you have k plus 1, here you still have k plus 1, and it's still valid. So what will you do now? You have to factor this out. Now by factorization, using factorization, you remember factorization, you factor this. How can you factor this? If you multiply 2 and if you multiply k plus 2 and 2k plus 3, hopefully we are supposed to get this guy, because you see you have 2k here and you have 7k plus 6, so you have to use factorization. Now, if you use factorization, you can use k plus 2 and then 2k plus 3 upon 6, because k multiplying 2k will give you this, k multiplying 3 will give you 3k, then 2 multiplying 2 will give you plus 4k, automatically have your 7k, then 2 multiplying 3 you will now have your 6. So you have this. So after having this, now you still want this to look like this. So how can we do that? We already have k plus 1 outside. Now if you look at this, you can split this to look like you have k plus 1, then this one and plus 1. If you open here now, it just give you k plus 2, which is this. Now the next thing you want to have, now here we have 2k plus 1. First of all, we have 2 into k plus 1. Now what should be remaining? You have 2 times k, we give you 2k. 2 times 1 will give you 2. So you are still left with plus 1 to give you this 3. So you close it upon 6. Now if you look at it, you now discover that if actually k plus 1 is a natural number, then this, if k plus 1 is a natural number, then you can say if k plus 1 is a natural number, because this stands for any natural number, then definitely here now we'll have n, here now we'll now have n plus we have 1, then here now we'll now have 2 into this place, now we have n, then plus 1 upon 6. So since you have satisfied all the 3 rules, if you remember our rules, you have satisfied p of 1, p of k, then p of k plus 1, then you conclude. And your conclusion, you always say that since it is satisfied, since p of 1 is satisfied, is true, p of k plus 1 is true, then pn is true for all integer n which is in n. What do I mean? Since p1 is true, p of k is true, then you now said so is p of k plus 1. Therefore p of n is true for all n, you now say may belonging to n, and that will be your concluding remark. I'm going to be fast. This mathematical induction, some example. Now remember, if we want to test, now what we are trying to do is that we want to show that this guy is equal to raised to power n, b raised to power n. We want to test if p of n is true. If this statement is true, remember we have to test the p of 1, we have to test the p of k, we have to test the p of k plus 1. Now It's very simple. I said P of 1 is to just insert 1 in the formula. There you have B and N. We have 1, then it should be equal to A of 1, then B of 1. This is obvious. This is obvious because it's true. Because what you get here is just AB, and here too, n raised to power 1 is that thing. So this is true. Now we have to check off P of K. We'll just insert K there. We have A raised to power K, we have B raised to power K. That's on the right hand side, because the left hand side gives us A, B raised to power K should be equal to A raised to power K, and then B raised to power K. But you know, from our law of indices, if you look at it, it's straightforward. We just have indices says we do this, B of K, A of K and B of K. So this is true. Now we just test for B of K plus 1. This is also true. Now what are we going to do here? This now, we're putting it on the left hand side, where it implies that we're going to have A, B raised to power K plus 1. This should be equal to A raised to power K plus 1, and then we now have B raised to power K plus 1. Now this is actually what we are trying to achieve at the end of the day. But now putting it on that left hand side, we have A, B raised to power K plus 1. Now what does it mean? What does this mean? It simply means that we are going to have the first guy raised to the power of K, and we're going to have the same thing, AB raised to the power of 1. By indices, we know that if they are the same, all we need is to add the power, and that's how we got this. Okay, and then remember from our previous P of K, we know that this simply means A raised to power K and then B raised to power K. Why, on the other hand, this other guy means A raised to power 1 and then B raised to power 1. Now, according to this other guy, what do we have there? What do we have there? We know that if we say we want to collect like collecting like terms, we have that A raised to power 1. This is multiplication all through. It's multiplication all through, so we'll now have A raised to power 1. Similarly, we have B raised to power K, and then we have B raised to power 1. Now what are we trying to get? By indices also, by indices, we know that A raised to power K plus 1, and then we now have B also raised to power K plus 1. So as required, this is what you required. This is actually what you required. So you now said if PK is true, and so P of K plus 1 is true, since P of 1 is true, then you now say Pn is true for all natural number that is in N. You just conclude if P of K is true, so is P of K plus 1. So and since P of 1 is true, then now said P of N is true for all N elements in N. Simple as that. Now this is another example. You say prove that for all N greater than or equal to 1, 1 plus 4 plus 7 plus you have 3n minus 2 is equal to n into 3n minus 1 all over 2. Solution, we have to test for P of 1 like I rightly said, then we have to check for P of K plus 1. This is the inductive step, we call it inductive step. Then now we need to check for P of K plus 1. Now you note that we have to add it to the left hand side and to the right hand side. So we have 1 plus 4 plus 7 plus we have 3k minus 2 but this time around we now have plus. Now where you see n, you put k plus 1, so you have 2 into k plus 1, then you have minus 2. Now when you put k plus 1 here, you put k plus 1 here, you evaluate, it gives you. But here now let's consider this one. And this one is the same thing as saying we have, this should be equal to this guy. We have k into 3k minus 1 all over 2. Then we add this guy to it. Now if we evaluate this guy, this is simply as saying we have 3k into upon 2 plus, let's evaluate this guy. See, this is, we now have 3k 3 plus 3 times 1, we now have plus 3, then minus 2. So that means this is simply saying 3k upon 2, then plus, we now have 3k plus 1. 3 minus 1 is 1. So similarly, like I said, look for the LCM is 2. So we now have k into 3k minus 1, then plus we now have 2 into 3k plus 1. Now subsequently, when we expand that guy, we expand this guy, what are we going to get eventually? Let's just expand. We have 3k squared minus k, then plus 6k, 2 times 1, then plus 2 upon 2. So what are we going to have here? We have 3k squared, then we have here, this guy will now give us plus 5k, then plus 2 upon 2. We factorize here, we have k plus 1 into 3k plus 2. You factorize. Factorization, this multiplied by this will give us 3k, this multiplied by this will give us 2k, by this plus that will give us 3k plus the 2k, we have 5k here, then 1 times 2 will give us this. If you don't know how to factorize, just comment down below, I will do that properly. Now, but we want this, as I said before earlier, we want this to look like this. We want to have k plus 1 into 3, then we need to have k plus 1, then minus 1. Now how can we get it from here? Remember, here we have 3k already with plus 2, 3k already plus 2. So we now say this is 3, this is k plus 1 first of all, which is our n. Then we now have open bracket, we now have 3 into, we need to have k plus 1 first of all, but we need to have minus 1. We need to have minus 1. Now, is this correct? You check. You have, when you have 3k, this place is plus, so you have 3 multiplied by 1 plus 1, you now have 3. When you now say 3 minus 1, you now have your plus 2 back. So this is the same thing as this. So you conclude the principle of mathematical induction for all n greater than or equal to 1, p of n is true. Since p of 1 is true, p of k is checked. Then by the principle of mathematical induction, you check if p of k plus 1, if it is checked, then you now said p of n is true. You conclude in that manner. If you have any question, any suggestion, and you need more examples, comment down below. Please subscribe and ask others to subscribe. I will get motivated and post more video. Thank you.